Welcome. Today we will discuss dynamic braking and regenerative braking of frequency variable voltage source fed induction motor drive. First we will discuss dynamic braking of PWM voltage source inverter fed induction motor drive. So, at the front end we have a 3-phase diode rectifier operating from 3-phase supply. Then we have the switch SW, then filter inductor and DC link capacitor for filtering the DC link voltage ripples. Then we have a switch S and a resistance RB, braking resistance in series. This is feeding DC voltage to the PWM pulse width modulated voltage source inverter, which is feeding the 3-phase induction motor. So, this is the voltage VD, DC link voltage across the PWM VSI, and ID is the current in the DC link. So, this is the figure of VSI controlled induction motor drive with dynamic braking facility. So, when operation of the induction motor to be shifted from motoring mode to dynamic braking mode, first switch SW is opened. Switch SW is opened. As switch SW is opened, then the regenerated energy from the VSI, it flows into the DC link and DC link capacitor voltage rises. DC link voltage rises, VD rises, as capacitance gets charged. When the capacitance voltage exceeds a specified upper limit, then switch S is closed. As switch S is closed, the resistance RB is connected across the DC link. Then the regenerated energy from the VSI and a part of the energy from the capacitance flows into the braking resistance R B, gets dissipated there. So, during this process the braking energy is utilized, dissipated in the resistance R B, and a part of stored energy from the capacitor also flows into the resistance R B and dissipated. So, capacitance voltage reduces. So, as braking resistance R B is connected across the DC link, V D reduces. So, when V D falls less than equal to certain V D star reference value, again switch S is opened. When V D falls below a set value, V D star reference value, switch S is opened. As switch S is opened, the resistance R B is no more across the DC link, switch that part is open, resistance is open. So, in that case the regenerated energy from the machine is dissipated in the charges the capacitor and capacitor voltage rises. So, in this way, by opening the switch and closing the switch S, the regenerated energy is dissipated in the braking resistance R B and dynamic braking occurs. This is the dynamic braking of the drive. So, this closing and opening of the switch S is based on the value of the DC link voltage. Generated energy is based on that, generated energy is dissipated in the resistance R B, giving dynamic braking. Next, we will discuss regenerative braking of PWM VSI fed interexploder drive. So, in dynamic braking, the machine operates as a generator and the energy is dissipated in the resistance R B. So, it is the dynamic braking, but in regenerative braking also the machine operates as generator, but the braking energy is not dissipated in resistance, it is fed back to the supply AC, is fed back to the supply. So, that efficiency of the overall system improves, braking energy is utilized effectively. So, first scheme, when the PWM VSI is directly supplied from a DC source, battery say. So, in this case, when the PWM VSI enters into the induction motor enters into regenerative braking mode, the direction of the DC link current ID reverses and flows into the DC source, and DC source gets charged. So, this scheme has the inherent regenerative braking facility in itself. So, when the VSI is fed from a rectifier for the drive to have regenerative braking feature, the front end rectifier is replaced by dual converter as shown here. So, converter 1 and converter has firing delay angle alpha 1 and converter 2 has firing delay angle alpha 2. So, the DC voltage that is fed to the PWM VSI Vd is always positive. Vd is always positive, that is the voltage supply to the PWM VSI. So, when the induction machine operates as a motor, so power flows from the source to the machine. So, ID is positive, motoring mode. For motoring mode, ID is positive. As ID is positive, converter 1 operates as in the rectification mode and converter 1 carries positive ID. When the machine operates into regenerative braking mode, then this current I D is negative. I D is negative. So, during this regenerative braking mode, converter 2 carries the load current. Converter 2 carries this I D. So, converter 2 has firing angle alpha 2 greater than pi by 2. It operates in the inversion mode. It operates in the inversion mode and power flows from the machine through the PWM VSI and converter 2 to the AC source. So, regenerative braking facility is obtained in dual converter fed PWM VSI induction motor drive. So, the recent alternative to dual converter is synchronous link converter. So, in this figure a scheme of synchronous link converter fed PWM voltage source in induction motor drive with regenerative braking facility is shown. So, PWM invert there are two PWM inverters, PWM inverter 1 feeds the induction motor and at the front end we have the PWM inverter 1 with inductance in each phase which is connected to the 3 phase AC source. Okay. So, as you see here the AC voltage at the terminal of the PWM inverter 1 is VI phasor VI and AC supply voltage is Vs and current drawn by the PWM inverter 1 is Is and the inductances are Ls in each phase. So, synchronous link converter is this PWM inverter 1 with inductance Ls in series of each phase. So, this is the synchronous link converter. So, how the scheme works let us understand. So, you see as you see in this circuit the phasor equation is supply voltage Vs equals to inverter terminal voltage Vi plus j x s into phasor Is. This is the phasor equation which is satisfied in this circuit. So, the depending upon the source current Is, Vi is controlled such that the PWM converter 1 always operates as a synchronous machine, synchronous either as a motor or generator. So, let us understand it. So, the synchronous link converter draws current from the supply which is at unity power factor and it can either draw energy from the source or it can feed energy to the AC supply, always at the unity power factor. So, the PWM inverter 1 is operated to produce a voltage V I of required magnitude and phase. So, that source current I s is nearly sinusoidal and in phase with V s for motoring and 180 degree out of phase for braking, giving unity power factor. This is explained in this figure phasor diagram. So, phasor diagram for motoring operation is shown in here. So, in the here V s supply voltage, the inverter 1 supply voltage, the AC supply voltage V s and supply current I s are in phase, and the V I is decided such that the phasor V I plus phasor V I plus J excess I s is V s, and V s and I s have to be in phase. So, V I is controlled with delta in this fashion for motoring operation. For generating operation, the source current I s must be 180 degree out of phase with the supply voltage V s. So, that unity power factor is obtained. So, in this case V I is shown as shown in this phasor diagram and the phasor equation is satisfied. So, V I, its magnitude and phase are controlled through the PWM inverter. So, how to control the magnitude and phase of V I? It is controlled because through sinusoidal PWM of inverter 1. So, because of sinusoidal PWM, magnitude and phase of V I depends on the magnitude and phase of modulation signal, and because of sinusoidal PWM, V I does not contain low frequency harmonics. The inductor L S source inductance filter or invert series inductance filters out the high frequency harmonics to produce nearly sinusoidal current I s. Since this PWM VSI behaves like synchronous machine and phasor diagram is also same for both, it is called synchronous link converter. when SLC fed PWM VSI drive is operating in steady state, power supplied by the synchronous link converter is equal to power taken by VSI 2. Since both VSI work independent of each other, this is achieved by closed loop control of the DC link voltage. So, at steady state condition, the power supplied by SLC equal to DC link supplied to the DC link equal to power taken by the VSI 2. So, capacitor voltage remain constant at the reference value VD star. So, in this situation, if load on the motor is increased, so if load on the induction motor is increased, power taken by the VSI 2 from the DC link exceeds the power supplied by the synchronous link converter. So, as power input is less and power output is more. So, VD DC link voltage falls below the reference value VD star, because energy is drawn from the capacitor. So, the closed loop control will increase the value of the supply current IS, and hence power supplied by the SLC to the DC link increases and DC link voltage is brought back to VD star reference value. So, this is in this closed loop control, the DC link voltage is maintained constant and hence always the operation is maintained as required. So, this will also give ride through capability during voltage sag and voltage swell. So, during a voltage sag, that means AC source voltage fall. So, during a voltage sag, the closed loop control maintains the DC link voltage constant at the reference value by increasing IS, that is drawing more current from the source. Thus, motor DC link voltage is maintained constant at the reference value. So, motor continues to be provided constant voltage and produces same maximum power and torque. So, for closed loop control of variable frequency, variable voltage source fed induction motor drive, a scheme is shown in this figure with regenerative braking facility. So, at the right most you have the PWM VSI feeding the induction motor and getting some drawing power from a DC source. So, the induction motor speed is taken feedback through a speed sensor and compared with reference speed omega m star and processed through a speed controller. In the speed controller output is processed through a slip regulator that decides the omega SL star reference value of the slip speed depending upon the motor current and speed, and then omega m is added with omega SL star, that is the reference, that is the synchronous speed omega s, and this omega s is 2 pi f. So, this is the frequency command for the VSI is obtained from here directly, and the voltage command is obtained by converting from omega s to V star by flux controller block, which adopts the V by F control strategy, constant V by F, then constant V strategy to generate the command voltage V star. Then actual motor voltage is taken feedback through a voltage sensor and compared with the reference voltage V star, and error is processed through a voltage controller that decides the modulation index M for the PWM VSI. So, the closed loop scheme can use either PWM VSI or any VSI or cyclo converter with little modification. So, it is applicable for all variable frequency, variable voltage sources. The closed loop control scheme uses outer speed loop and inner slip speed loop with a slip limiter, as you can see from that figure. Since for a given current slip speed has a fixed value, the slip speed loop also functions as current control loop, inner current control loop. So, slip speed control ensures that motor operation always occurs in the portion of the speed torque characteristics between the synchronous speed and the maximum torque point, thus gives high torque to current ratio. So, slip regulator sets the omega SL star reference value of the slip speed such that its maximum value limits the inverter current to a permissible value. Inverter current is limited by the omega SL star, and this relation, that is omega m is omega m, omega s is omega m plus omega SL star. From this inverter frequency f is determined and machine voltage V star is also determined according to V by F control strategy. This drive has fast response because the speed error is corrected at the maximum torque. So, drive has fast response because always maximum torque the maximum torque speed correction occurs, and direct control of slip assures stable operation under all operating conditions. So, this is a very good scheme. Closed loop control has very good performance. Thank you for attention.